Welcome back. In the previous section, we ended off talking about strictly monotonic functions. Those are functions that are either always increasing or always decreasing. And the reason why we wanted to talk about them is it actually has a connection to this theorem, the one that tells us when we have an inverse existing. So firstly, a function will have an inverse if and only if it is one-to-one. So that means if you know that you have an inverse, then you're guaranteed that the function is one-to-one. And also, if you know that a function is one-to-one, then it must also have an inverse. So this is a two-way street for part one. The second statement is not. It's a strictly if-then statement. So if you have a function that is strictly monotonic, then you're guaranteed that things are one-to-one and therefore invertible. So that is definitely true. So if you can show that a function is monotonic, strictly monotonic, then you can conclude automatically that it must be a one-to-one function and is therefore invertible. If we'd had this theorem actually earlier, we would have had a much easier time in 5.1. If you remember when I was showing the natural log was a one-to-one function, I had to do a little bit of working to show that it was one-to-one. But we also showed back in 5.1 that natural log is strictly increasing. It's increasing over its whole domain. So had we known this theorem, we'd be able to say, since natural log is always increasing, then natural log is one-to-one. Of course, we're going to come up to a nice conclusion later on. We're going to come back to this idea and say, therefore, natural log will be invertible. But for now, we're going to just talk about this theorem sort of separate from logs. So if you have an inverse, then you'll be one-to-one, and if you're one-to-one, then you'll have an inverse. Same is not true for being monotonic. If you are monotonic, then you will have an inverse, but if you have an inverse, you do not have to be monotonic. So the thing that we're probably thinking of, and the reason why, if you're thinking like, how is that even possible? How can you be invertible but not also strictly increasing or strictly decreasing? You're probably thinking of a function that's nice and continuous. But if your function is not continuous, then you can be invertible even if you are not strictly increasing or strictly decreasing. So for example, think about the following function, and this is not a very exciting function, but so be it. It's a straight line, and then we have a little discontinuity, and there we go down to there. So this is something where we definitely have a function defined on a domain. It's definitely a one-to-one function because every y value that we have in the range is used exactly once. There is no pair of x values that give me the same y value. I have a y value there, but that's a hole down below. So this would be a function that is invertible, but it is also a function that is not strictly monotonic. It increases for a while and it decreases. So that's sort of the plot twist there. If we have a function that's discontinuous, you could be invertible, but also not strictly monotonic. Probably not a big surprise, this little corollary here. F is invertible if and only if F inverse is one-to-one. The reason for this one is if we know that F is invertible, then F inverse also has an F inverse. In other words, F inverse must also be invertible. And if F inverse is invertible, then F inverse must be one-to-one. So that's sort of a nice little conclusion that comes from our theorem. We have our horizontal line test that we had from back in pre-calculus days. So you would have learned this little definition for how to tell if something is a one-to-one function or how to tell if something has an inverse. You have a function will have an inverse if and only if you pass the horizontal line test, if horizontal lines cross your graph in at most one point. This is basically just a consequence of the previous theorem. If you had the horizontal line cross your graph in more than one place, then you would not be one-to-one. And if every horizontal line crossed in at most one place, then that would be telling you that there's exactly one x value for every y value. In other words, it's telling you that your function is one-to-one, and if you're a one-to-one function, you must be invertible. Pre-calculus, we remember this too. When we were finding inverses, it was just a matter of exchanging our x's and y's, and that's because of that earlier theorem. We said that, if AB was a point on F, then BA would be a point on F inverse. So not a big surprise that we'll need to, at some point, interchange the x's and the y's. And once we've solved for y, good for us, we found ourselves our inverse. And we'll also remember that whatever we get for the domain of f inverse must have been the range of f, and that's because we're swapping the roles of inputs and outputs. So once we know what the domain, once we know what f is and we know its domain and range, you also automatically would know the domain and range of f inverse. Whatever the domain of f is, that's the range of f inverse. Whatever the range of f is, that's the domain of f inverse. And then at the very end, you should always confirm that you're right, confirm to see that f composed with f inverse does give you x, and the reverse also true, f inverse composed with f does give you x. Okay, so here's one. The first part is for us to confirm that this function has an inverse, and then the second part is for us to actually go ahead and find that inverse. We could confirm this sort of in the same way that we did earlier. We had an earlier problem where it was a nice little cubic function, and we showed that it was a one-to-one. We supposed we had the same y values. We got the same x values. We had our conclusion. And we could do that too, right? Because if we showed that our function was one-to-one, then automatically that would be enough to show that it's invertible. But I'm going to be lazy, and my laziness is going to involve derivatives here. I know what f looks like. It's a cubic function, and I also know what f prime should look like. So using the derivative rules that I know before, the power will come down, the power will get reduced by 1, and derivative of the inside is just 1. So that would be my first derivative. The thing that I'm going to note here is that for every x, f prime is going to be greater than or equal to 0. When x is equal to 1, that is the one and only place where our derivative is 0. Every other place our derivative is positive. So we don't really have any places where this function is strictly constant. It is always increasing. So f of x, or our original function, is always increasing. In other words, it's strictly monotonic. And if it's strictly monotonic, then therefore we know that f is invertible. And that is courtesy of the previous theorem. Remember that we had two parts to that theorem. One was that our function had an inverse if and only if it was one-to-one, but we also had that if our function is monotonic, it is one-to-one and therefore invertible. So here we showed that our function was always increasing. It was strictly monotonic, so it's a one-to-one function. It is also invertible. And so now to find f inverse, easy enough for us to do, we're first going to rewrite our function as y equals. And then we exchange the x's and the y's and solve for y. So I have x is equal to 4y minus 1 cubed minus 7. And then the only thing left for me to do is just solve for y. And not hard to do, bringing the 7 over, dividing by 4. And then to finally finish things off, cube rooting. That would give me y minus 1, so y would be 1 plus this cube root. So now that I've isolated and solved for y, I can say that that should be my inverse. That should be f inverse. And that is 1 plus cube root of x plus 7 over 4. If I wanted to think about domains and ranges, I know for this function that this is a function whose range is all real numbers, which means for this function its domain should be all real numbers. The reason I know that the range is all real numbers, it's a one-to-one function. It's always increasing. I know what the graph looks like. It's y equals x cubed, slightly stretched. I know that the range is all real numbers. So for this function, its domain is all real numbers. If I wanted to, and I'm going to leave this as an exercise for you to do, I should confirm that f composed with f inverse will give me x, but I will promise you now that yes, it certainly does. But I'll leave that as an exercise for you to do. We've got a nice theorem here which has the relationships that we want to now talk about between f and f inverse. So here we're assuming that there's some sort of an invertible function. And here's the nice part about relationships between f and f inverse. If f is continuous, then so is f inverse. And if f is increasing, then f inverse must be increasing. If f was decreasing, then f inverse must be decreasing. So in other words, f and f inverse are going to share a lot of properties. They might have different domains. That's the one thing that might be different. So f will be continuous on its domain and f inverse will be continuous on its domain. They may not be the same domain for each. So just be aware of that. The big one, the one that's really important for us though, is that if you have a function that's differentiable, then f inverse will be differentiable too, provided that we're looking at an interval where f prime of c is not 0. So places where our function doesn't have a horizontal tangent line. If our function has a horizontal tangent line, then f inverse won't necessarily be differentiable at whatever that point happens to be. But if we've got a function whose derivative is never 0, then its inverse, and if it has an inverse, then its inverse will always be differentiable. So if we're just sort of sliding back to the last example for a minute here, we know that for this function, f of x, we confirmed that its derivative was always going to be greater than or equal to 0. And I said only when x is 1. That's the only place where the derivative is 0. That means that that's going to be the one and only time where f inverse won't have a derivative. So f inverse should have one place where it's undefined, and I would know where that would be. It would be at whatever f of 1 is. If I were to figure out what f of 1 is as a number, that would be the location where f inverse's derivative would be undefined. So now if we know all of this, and we know stuff about natural logarithm, we can already predict what we should expect to see for the inverse for natural logarithm. Because we know it's definitely going to have an inverse. It's a monotonic function. We proved that right at the beginning of 5.1. So definitely there will be an inverse. And so what we know is for natural log of x, the domain was positive values and the range was the real numbers. So that was our function natural log of x. So that means that our inverse, and I'm not going to say the inverse is e to the x yet because we haven't said that it is e to the x yet. So I'll just say this mystery function, we're trying to figure out what it is, f inverse. Its domain should be all real numbers and its range should be only positive numbers. So whatever the domain was for f, that's the range for f inverse. Whatever the range for f was, that's the domain for f inverse. Since f, we said that that was always increasing, which means f inverse should also always be increasing. So that means that even though we don't know what f inverse is yet, we know its derivative will always be positive, and that's because for f, its derivative was always positive. As far as continuity goes, f, the natural log, that's continuous on its domain. And so since f is continuous on its domain, then when we finally figure out what the inverse is of natural log, we'll know that it is also continuous on its domain. As far as differentiability goes, we know that f prime exists for every x in the domain. The other thing that we also know is that f prime is never equal to 0. Remember that our theorem said that if f was differentiable and also not equal to 0, then f inverse would have a derivative. And so f inverse always has a derivative and it's never 0, which means f inverse should be differentiable on its entire domain. So there shouldn't be any places where f inverse does not have a derivative.